Hello, everyone. My name is Ihnat Zharikhin. I am presenting a presentation on the topic integrated microlenses for efficient light extraction from nitrogen vacancy centers in diamond. My mentors are Roman Kumar, Artur Lozova, and Carlos Meriles. Thanks to them for helping me in everything. Okay.
Stop working again? It just maybe with some delay flags.
Okay. This just
Okay.
So you probably all know that a diamond is a lattice of carbon atoms that are arranged in some particular way, all right? But actually in this lattice, there are some defects. For example, some carbon atom can be replaced with some other atom, for example, a nitrogen, or it can be even replaced with just empty space, so no atom. Okay, so imagine that there are two defects right next to each other, nitrogen and a vacancy, so empty space. This thing is called a nitrogen vacancy center or an NV center in a diamond. Okay, so one of its main properties is that it is photoluminescent. So if you if you shine on it with some light, which happen to be electromagnetic waves with which happen to be light that has a wavelength with a green color, then it emits red color. So when you're excited with green color waves, it emits red color. And actually, it emits a spectrum of waves like this. But human eye see this as a red color. Actually, this defect is sensible. So, for example, if you influence this defect with some microwaves, then the light that you can get from it is now more dim. So it's like darker. It's still red, but it is less amount of it. So what can be the NV center used for? First thing that it can be used for is quantum memory and processor in quantum computing. The second thing is quantum sensing. As I already mentioned, it can sense things that influence it, and because of it, it emits different light. And so we can sense light that it emits, and because of it, we can understand what influences it in the microenvironment. For example, it can be temperature, electric or magnetic field. And also it can be used for quantum communication. Okay, so we know that it emits some light and we need to get it to understand something. But because of high refractive index of the diamond, which is 2.4, we only get a small amount of light. So you see, this is light rays, and they go here and they reflect, they refract and go not in our objective. And actually we get only this small amount of light that it emits, which is bad because we can poorly sense what it emits. So for example, if with some different influencers it emits light that is different a bit, we cannot sense it because we sense only a small part of the light. So this is what we do. We try to put a lens on top of the diamond so that it will focus light and our objective will see more light. We simulated this using a program called Console, and then we analyzed the data using Python. The objective is right here, Well, actually, you may ask why we can just put objective right next to a diamond. It's because we use also this objective to excite the NV center. So we don't use two objectives because it is much harder. So we shine green light using also this objective, and then sends red light. So here are the results of the simulation. This is a heat map of the electric field at every point. And the amount of light we get is proportional to square of the electric field. So here we can see that we get here little to no light. And here with some microlens that is with the refractive index of 1.5, we get a little bit more light here. And but then when we raise the refractive index even more, we can see we can easily see that there are much more light coming in the direction of our objective. However, the last one is not really real because here we have refractive index of 2.4, which is the refractive index of a diamond, and we won't make our lens of a diamond because it is very expensive. Here is the animation. You can see how it becomes better. And here is the plot. How we got these values. We integrated the data over the small line here, which is basically what our objective gets. And we compared it to the case without any lens. This is, we say that it is here. So like no lens, we can say that it is like just air here with a refractive index of 1. And you can see that this plot rises, which is what we expected, and the most real values of refractive index at which we can have our lens is around from 1.4 to 1.6, and we get here around 2 times more light than without a lens. Also, what we did is we tried to simulate a circular or spherical lens instead of hemispherical, and as you can see, it clearly also focuses more light. The fabrication of these lenses were also made in Carlos Meriles' lab here, and you can see these lenses here. They are around like 10 micrometers in size, and the preliminary results show here with the lenses of it is polymer lenses, so their refractive index is 1.5. You can see here that it is around 2 times more light than without a lens. So in conclusion, we studied the light extraction problem from NV centers in diamond using COMSOL and Python. We simulated hemispherical lenses with different refractive indexes, and we saw the correlation between the amount of light we get and the refractive index of a lens. Also, a spherical lens gets more light than a hemispherical. And the fabrication and experimental results with these lenses showed that we predicted the result right, and it is around 2 times more light with lens than without. In future, we can simulate other different geometries of a lens and simulate more realistic light source, which is actually more like a dipole. Thank you for listening.
check it out.
I'm sorry that my questions would be like in more theory, but I really would like to know about what I will ask. The first question is you have used the role of first diamond, and how would it affect if you use other type?
What do you mean? Which diamond roller?
Ты использовал гребень и нет минералов.
Мы использовали. We used diamonds that are grown in a lab. Yeah, so not real ones from Earth.
And how do you think what would be happening if you use a raw diamond?
Well, if we use a raw diamond, there are actually in diamonds that are in Earth, there are a lot of such defects, and there can be like really many other defects, and the results are like our light can, for example, get absorbed by another defect or something. So, and we like cannot really predict what will happen.
The second question, can you please return to the second slide?
This one.
Yeah. I really would like to know if you have some chemical or physical explanation how exactly changing the carbon atom to nitrogen creates this empty space.
Okay, I know a little bit. I can say it. So when there is a nitrogen atom, it has, for example, other number of electrons. So here it is energy level graph. So it creates another energy levels for electrons. And if we have no defect, then if even photons get to the electrons, they do not jump from a ground state, energy state to excited energy state. So the light just goes by. And if there are more energy levels that come with the defects, the electron can jump from this level to some other and back. So, and because of it, the light gets absorbed. And when electron jumps back, then this is when this red light is emitted. Does this sound? Okay.
Well, my first one,
Thank you for the great presentation. And you mentioned the simulation for microlenses refractive index about 2.4. And you mentioned what this is refractive index of diamond. That's why it's not very useful to use diamond because it's expensive. But did you consider using of thin selenite? Because it's well-known material with refractive index of 2.4 as well, and it can be well machined, and it's like can be it can have some use for these purposes.
Well, I don't know, to be honest, we didn't think about it. So
Okay, thank you.
thank you. Let's see. Okay, yeah, go ahead. Sorry, I didn't see your hand.
What did you enjoy the most about the project?
I enjoy the most debating about theory in these like atoms and states with my mentors.
What was the most delightful moment in your project?
Delightful.
Maybe when it was the most the happiest moment.
Well, I was happy when the results from the simulation matched the results from the experiment.
Okay, sure.
Thank you.